So we have two types of energy that we deal with in physics, potential and kinetic energy. And in this particular video, we're just going to talk about types of potential energy only. So just this category of potential energy. And as we discussed in another video here, potential energy sort of refers to stored energy or energy with some ability. And of course, that ability here is to cause some action to happen. Like some effect, a car is going to go faster, a can's going to crush it, whatever the case may be. So these are types of potential energy here that we'll deal with. Okay, the first type is probably the most common here. It's called gravitational. And what that's about is something like this. Suppose I had a soda can right here, and I had a huge brick above the soda can. And I released this brick, it fell down, and the soda can is going to be this thin thing like that, and there's going to be this big brick sitting on top of it. The block here has crushed the soda can. So in other words, when it's being held above the ground, it has so much energy, potential energy, that energy is released in crushing the can. So there's your first type of energy right off. What you have to do to measure the gravitational potential energy, let's say gravitational potential energy of this brick here, is you have to see, well, how high was it off the ground? Typically some distance h like that. And the potential energy, usually the textbooks use the symbol U like this, U sub gravitation, or it might even be easier just to call it PE sub gravitation for potential energy. And in this case here, the physics definition, the operational definition is m times g times h. This is the potential energy of any object of mass m, a height h above the ground, given that g is the gravitational pull of the planet. For Earth, of course, g is 9.8. This will give you the potential energy in joules of an object lifted up above the ground like that. That's the first type of gravitational potential energy. One word of caution on using this equation here is that h here, remember, is always going to be the vertical height. Never any other height. It's just the straight height above the ground. So you shouldn't let that yourself get confused depending on the types of problems you see. For instance, you could have a hill like that undulates up and down like this, and if there's a ball or a car right here on the top of that hill, the way you would measure the potential energy it has, and it looks like it does have potential energy because it can roll down and speed up, is you'd figure out where the ground level is, say something like this here, and the potential energy would just be straight, that h right there. Or not the potential energy, the height above the ground, but of course the potential energy then would be mg times that quantity. And of course, as the ball falls and goes down to the ground, it might be all the way down here on ground level, in which case h becomes 0. So there is no potential energy left right there because h is 0. But then it can sort of rise up along this little hill right here, and of course the h is going to be different. But again, it's always that vertical h straight above the ground like that. All of these things have potential energy. So this is height like h1. This is height h2 over here. You could certainly get it and start labeling these things. The potential energy right here is mgh1 and mgh2, something like that. So there are different potential energies, and indeed at all these levels can have one. So that's what potential energy is. Gravitational potential energy. The next type of energy that there is, potential energy that we have, is spring potential energy. And it's important for this class because we deal with springs and what springs do and that sort of thing. So let's just get into it then. There's another video that talks about what springs are. In particular, springs always have a fixed end like this, and they're all curly like that. And when springs have some equilibrium position, this is the equilibrium position right here. We discussed in another video here that the force you would say present on an object is 0 at this equilibrium position, because the general force law that we're concerned with here is 1/2 k times delta s. And that's not even right. That's not the force law. The force law is minus k times delta s. Pardon me, I'm getting a little bit ahead of myself. That's the energy equation. So this is the force law here. So if the object is not displaced from equilibrium, delta s is 0. That means the force would be 0. But of course what happens now is, suppose we took the spring and we stretched it like this, stretched it all the way out like this to this point right here. In other words, we displaced it from equilibrium by a distance delta s like that. Then of course the force is going to take over because the spring wants to pull us back and restore itself to equilibrium. But alternatively, you can think of a spring, particularly if I'm holding it here like this, say with my hand, I've got to sort of hold it, maybe my hand will shake a little bit if it's a really stiff spring. But if I abruptly let go of the spring, it'll go back and go twing like that. We can use it to launch a little projectile across the room, which is what a slingshot is, or something like that. But there's energy stored in a expanded or compressed spring. So the potential energy of a spring then is 1/2 k times delta s squared. That's the equation I was trying to write earlier instead of force. But this is the potential energy stored in a spring, and it also gives the energy in joules. So once again, almost like the force law, which is minus k times delta x, a spring that has a spring constant k, just multiply by half, and your concern primarily is how far is that spring displaced from equilibrium. There it is right there, delta s. So of course, if delta s is equal to 0, then u is equal to 0, because that means that the spring is at equilibrium. It's not presenting a force or anything, it's not storing any energy, but as soon as you displace that spring from equilibrium, say, and delta s here becomes some other number that's not equal to 0, then you will have some potential energy. You will have some potential energy in the spring whenever it's expanded or compressed away from its equilibrium position. So the same thing will sort of hold here. Here is an example of two springs that are currently storing potential energy. So here's a fixed wall here. Those are fixed into a spring. And I'll just say in the middle here, draw where the spring would like to be if it was nice, relaxed, in equilibrium position. There's a spring right there. And I'll draw this dotted line here denoting the equilibrium position. Now there's two things you can do to a spring. Of course, you can compress it and you can expand it. So suppose I took this spring here and I pushed it like crazy so it was all bunched up like this, and this end of the spring right here was distance delta s from equilibrium. You can imagine this spring is storing a lot of energy because I pushed it all the way in with my hand, and maybe I'm shaking a little bit, and if I put a little block on the end of it and let go, it could launch the block through the air, that sort of thing. So this spring in this case here has potential energy stored in it. 1/2 k delta s squared. Definitely has some potential energy in it. That's a compressed spring. But the same thing holds for an expanded spring. So I take the same spring and pull it all the way out like that with the coils get all deformed, and I've expanded it once again some distance from equilibrium, delta s. This spring up here also contains some potential energy, 1/2 k times delta s squared. Now I'm using a lot of real similar symbols in this stuff here. Delta s and delta s here and here. Of course, the delta s's could be different. In other words, the amount that I compress the spring can certainly be different by the amount that I expand the spring. But in either case here, this spring and this spring here are both displaced from equilibrium. And again, that's what delta s is here. That's the spring's displacement from equilibrium, where the spring would like to be. And as long as you do that in a spring, whether it's an expansion or a compression, the spring will store potential energy. And of course, the equation one last time is 1/2 k delta s squared, potential energy of a spring.